Everyone, I'm Pan. Today I will introduce the low default prediction project. And the goal is to determine whether a loan applicant is likely to default based on feature such as age, education, income, employment, assessment, and past default history. And our testing data set has 9,000 and our training data set has 36,000 records. We explored variable correlations among the features. Loan interest rate and loan percent income has the highest positive correlations with loan status, and this suggests that higher interest rates and a higher percentage of income spent on loans are associated with a higher likelihood of default. Other variables such as person age, person income, and credit score show weak correlations, and understanding facial relationships help us refine our model and improve accuracy. And then we performed basic data cleaning, including checking missing value to improve our classifier's performance. And we focus on feature engineering and model selection. Since machine learning model like XGBoost and random forest require numerical inputs, we need to convert categorical features into numbers. So we applied label encoding, which assign unique numerical values to categorical labels. This ensures consistency between the training and testing dataset, preventing mismatches during prediction. For numerical features, we used standardization, which scored all values to common range. Standardization is crucial because it prevents large-scale features from dominating the model and improve the performance or of gradient-based algorithms. To evaluate model fit and stability, we test different validation strategies, including tenfold cross-validation and a simple string test split. We found that a simple string test split produced more stable results. We tried three different test set of proportions and observed that when the test set was set to zero point 0.1 of the total data, the model achieved the best predictive performance. This suggests that a smaller test set model generalizes better when maintaining strong performance on unseen data. Another major challenge was class imbalance, as most applicants in the dataset did not default. This imbalance could cause the model to favor the majority class. We applied small to generate additional synthetic samples for the minority class because it directly increased the amount of training data, improving the model's ability to learn from the minority class. Class weighting adjusts the importance of each class during training, making the model pay more attention to the force, but it didn't. It doesn't introduce new data. Threshold tuning help balance predictions at the decision stage, but it relies more on already trained model. However, the model trained on small processed data did not achieve optimal prediction results, possibly because the test data set remained imbalanced. We then use PyCal to compare multiple models and identify the top performing ones. So we select XGBoost, Light GBM, Random Forest, and Gradient Boosting for further optimization. So here's the code, XGBoosting and Light GBM and Gradient Boosting classifier. So according to the final F1 score, XGBoost is the best fit model. XGBoost has the highest F1 score, showing a good balance between precision and recall, and it handled class imbalance well and included built-in regularization to prevent overfitting. In business application, this reduced false positives, lowering the risk of approving high-risk borrowers. At the same time, it minimized false negatives, ensuring credit-worthy applicants were not wrongly rejected. This improved loan approval strategy and reduced financial risk. And Light GBM performed similarly, but had a slightly lower F1 score. Its faster training speed made it suitable for large data sets. However, it overfitted more easily, increasing the risk of incorrect loan approvals. And random forest remained stable and resisted overfitting, but did not match active boost performance. Gradient boosting showed weaker results, likely due to its sensitive to noise. We also used a grid search and OptiTune for hyperparameter tuning. After optimization, our model achieved an improvement in average score, leading to a better prediction accuracy. And XGBoost, the best model's learning curve shows a great fit, but indicates a slightly tendency toward overfitting. The training score remains at 1, showing that the model perfectly fits the training data, and the validation score is slightly lower, but follows an upwarding trend as the training size increases. The gap between these two scores is small, suggesting the two models generalized well and benefits from additional data. Confusion metric is crucial in assessing false positives and false negatives. In a low approval settings, a false positive means incorrectly proving a high score borrower. This could lead to financial losses, while a false negative could result in lost business opportunities. And the model shows strong performance, but recall is slightly lower than precision. This means the model misses some actual defaulters, uh, prioritizing precision over capturing all positive cases. The precision recall curve illustrated the trade-off between precision and recall at different decision thresholds. The model maintained high precision across all most recall values, but as recall approach 1, precision drops sharply. This indicates that the model effectively identifies defaulters with minimal, minimal false positives, but attempting to capture all defaulters leads to a significant increase in false positives. The high AP score suggests a strong balance between precision and the recall, allowing the model to distinguish defaulters from non-defaulters effectively. And thresholds adjust should align with business goals to minimize loan default risk, lowering the threshold improve recall to reduce unnecessary rejections of creditworthy borrowers, raising the threshold maintain higher precision. And the model achieved a high AUC score of 0.68 and 98. The ROC score stayed close to top left corner, which suggests that the model maintains a strong balance between sensitivity and specificity. Additionally, the curve remains far from the diagonal, confirming that the model makes reliable predictions rather than random guesses. If we have more time and resources, we would incorporate external data like social media and digital behavior data. This can help improve model, especially for borrowers with limited credit history. And in prediction, we can implement data drift detection, comparing new data distributions with the training set to ensure model adaptability. We can also set up a feedback loop that incorporates newly labeled data for continuous improvement. We can track key metrics like F1 score and so on, and use A/B testing to evaluate model adjustment. Overall, the current best model performs well, but can be further refined to better align with real-world business applications, balancing risk management, prediction accuracy, and operation efficiency. That's all of our content. Thank you for listening.